Hey, physicists, I just wanted to take a couple of minutes to define one more term for you. We had gone through work as the work energy theorem and also the definition of it earlier and did not get to the word power. And I wanted to do that just really quick so we don't have to do it in class on Monday. So just a couple of reminders here. We know that work, there we go, is equal to the change in energy that happens. So that means that it's got to be in an open system, not in a closed system. Let's see if I can get my stylus to go here. There we go. So we know that work is equal to change in energy, and we also know that we can define that as force times distance, where, again, the force and the distance are in parallel directions, or as your book says it, force times distance times the cosine of the angle theta between them. So that's all well and good. Anytime you're putting energy into a system, you have to do work to it. If you're taking energy out of a system, then you have negative work that is being done to the system. So that's fine, but there's one more piece of that that kind of helps to shape how work is done, and that's how fast it is done. If you imagine lifting a rock, you can lift it really fast, or you can lift it very slowly. If you run up the stairs, you can run up really fast, or you can run up really slowly. And in that process, you are changing the amount of energy in the system the same amount regardless, right? Because the change in gravitational potential energy would be m times g times h. There is no talk of speed or rate in that equation. The situation when time comes into play is when we start to talk about the power. So this can be the power that's generated from a system. If we've got something like a generator, right? Something that's getting power or taking energy from something, or it can be the power that we're putting into a system. It just depends on, again, which way we're talking about that change in energy. But power is marked with the letter P, and not to be confused with momentum, which is the little p. Power is with a capital P, and power is simply just the rate at which work is done. So it's work per time, okay? So if we think about the units of that, the units of work, well, that's measured in joules, and the units of time, that's measured in seconds. A joule second is also known as a watt, okay? What's that? That's right, exactly. Power is measured in watts. Okay, you can also say it in joules per second if that makes you happier, but either way, that is the unit of power. Okay, pretty straightforward, pretty simple. Once you understand the definition of work as change in energy, then it's pretty straightforward. I am going to throw one more piece in there just to make sure that we've got all of it covered here, and that is to remind you, we wrote it up there, that work is force times distance. I'm going to go ahead for this definition and assume that that force and distance are acting parallel to one another. If they're not, then of course you have to take the components that are acting parallel. And if I do force times distance over time, we can notice that that distance over time, well, that really is velocity, isn't it? Distance over time, assuming that the rate of change is the same, right? That there's no acceleration. We can say that a force acting times the velocity, okay, can give you also the power that is being generated. So just another way to look at that, if we look at the units here, we've got newtons and we've got meters per second. A newton meter is a joule. A joule divided by a second is a watt, okay? So just a couple of different ways to define power, depending on what units or what givens you are presented with in a problem. We like to do a lot of this with graphs as well. You'll see some of that in your homework. If you have questions, of course, please let me know. I do want to look at one quick task with you just to make sure that the definitions are making sense here. So we've got Amanda and Bertha in a car race. Their cars have the same mass, so that's helpful to know. Okay. At one point in the race, they both change their speeds by 10 meters per second in 2 seconds. It says to ignore air friction. Okay. So I am assuming, oh yeah, it says right there, I just needed to look a little bit more carefully here, that this is Amanda's car and here is Bertha's car, right? We've got our A and our B. Is the work that Amanda's car does while speeding up greater than, less than, or the same as the work that Bertha's car does while speeding up? Well, we can figure that out. We've got work is equal to change in, oops, there we go, change in energy. In this case, we're not talking about gravitational potential energy. Really, it's just that kinetic energy. So we can say that this is, come on, stylus. Oh, friends. There we go. Is equal to the change in kinetic energy, which is the final kinetic minus the initial kinetic, just making sure everybody's with me here. So that's 1/2 m times v final squared minus v initial squared. Remember, we can't do final minus initial quantity squared. It's not the same thing. Our math teachers will get really, really crabby with this, right? So if we look at Amanda, Amanda's final velocity is 20, so that's going to be 20 squared minus 10 squared, which is going to give you about 300. For Miss Bertha, her final velocity is 30, so that's going to be 900 minus 400, which is going to give us a value of 500. So it appears that even though they have the same change in speed, they do not have the same work done, because the kinetic energy that Bertha starts with and ends with are higher than those for Amanda. So if we answer the question clearly, it says, is the work that Amanda's car does while speeding up, it is less than, it appears, the work that Bertha's car does. You say, great, we did that a long time ago, Carveling. Why are we doing this? Because part B is where we care about it. It says, is the power generated by Amanda's car while speeding up, slowing down, or while speeding up, greater than, less than, or the same as Bertha's? So now we have to get out our power formula. We know that power is equal to work per time. And in this case, it's not a very deep question, but again, just to make sure that we can apply things, they both those changes in speed are happen over 2 seconds. So for Amanda, she's got that work, and again, this isn't the value of the work, but it's a representative number, 300 divided by that 2, whereas Bertha's got 500 divided by 2, and regardless of what those numbers mean, we can see that because the time is the same in this case, we can see that the power generated for Amanda is less than the power generated by Bertha, okay? The key here, friends, is that you need to pay attention to that time. If the time is different, then the power can also be different. Take a look at that. Go look at those homework questions. If you have things that you would like to discuss in class, certainly let me know. Otherwise, I will see you soon.